Okay, so good afternoon to all. So in the last class, we discussed about hardware, software, core design, and program modeling. So just I will brief it out what we have discussed in the last class. So in the last class, we discussed about how the traditional hardware and software partitioning is done at the early stage. Okay, so now in the when it is designing in the early stage, so what will happen? So when they are doing the hardware team is going to be doing the hardware design, and the software team is going to design look after the software design. Now, to do those particular design, the hardware engineers is going to look after for the hardware. Your software engineers is going to look up for the software. So now, when you are going to this particular partitioning will be done at the early stages of your hardware design. Okay. So now, what are the different issues which you are going to have when you are going to have the designing at the earlier stage itself? So there will be less interaction between the two teams, that is your hardware team as well as the software team. So now, whatever the operations it is going to happen, whether it may be a hardware design or it may be a software design. So it may happen serially or parallelly. Okay. So now, next comes the question, what is the limitations in that one? So if I do it separately and we are doing when they are going for the marketing, they have to integrate both software and hardware and they have to test it, whether they are working fine or not. We have to go, we have to check for that one. So when you are doing all these process, so the time to market will become more. So when the time to market, that is the product which you have been designed, if it takes more time to go to the market, what's the problem you are going to have? So what we are going to face? So there are many competitors which will be there in the market. So somebody may know what you are doing and they may come up with a new solution at the early stage itself when they are doing it parallelly. So these are some of the issues which we need to find. So when you are dealing with your hardware software co-design. So this is nothing but what? So your hardware software design is nothing but a problem statement. So when this particular statement, in this particular statement, we are going to try the problem statement in real life. Which are the different issues we are going to come across this particular designing of your hardware embedded system. Okay, so when you are talking about the embedded system, we are going to talk with respect to both hardware as well as the software. So now next comes the questions, what are the different fundamental issues which you are going to face in hardware software co-design? So the basic fundamental issues which you're going to get in your issues in hardware software co-designs are, first one is selecting a model. Okay, so the first one is selecting a model is the first issues which you are going to have. Second is selecting the architecture. So we are going to have the select architecture. So selecting the architecture will become another issue. So next is which language I have to make use of. That is, third will be your selecting the language. What type of language I have to use, whether I have to use the C or C++ or Java, or what if you are going with the hardware part. So which one, whether I have to go with the VSDL or whether I have to go with the Verilog. So next one is partition system requirements into hardware and software. So the next issues which are going to have is I have to partition the embedded system into hardware and the software. So partitioning the system requirements with respect to hardware and software is the next issue. So we will discuss one by one, starting from here, selecting the model. So now when it comes to selecting the model, so in your hardware software co-design, so here, what do you mean by model? So here the models are nothing but what? So models are basically used for capturing and describing the system characteristics. What are the system characteristics are there? So it's going to capture and describe the system characteristics. So that is nothing but what? So if you take your SDLC, normal software development lifecycle, you have studied, I think, right? So which is the first stage which you are going to have? The first stage which you are going to have in your SDLC lifecycle is your requirement and specification. So there I am going to tell what. So I'm going to tell you that what are the functional requirements and what are the non-functional requirements which you are going to have. So basically in your software development life cycle. So it tells you that what should be my characteristics of my design. It is going to describe you the system characteristics. So in this particular selecting the model. So in the selecting a model, what will happen in the requirement and specifications? So it is going to be a formal system. So that means it is going to be a formal system which consists of the objects and composition rules. So it is going to have the formal system which will be having the objects as well as the rules to be compromised. So it is going to have the objects as well as the rules. Now here it is making it is hard to make a decision which model to follow in a particular system or design, because that particular design depends upon your requirement. So because if you are going with a, for example, if I'm going with a building a airbag embedded system, then there the requirement is different. So if I'm going with the air conditioner, then there the requirement is different. So if I'm going with a oven, then the requirement may be different. So now, depending upon the different embedded system it is going to make, it will become a particular model to be used a difficult. Okay. So then it will make it hard to make a decision which model I have to make use of at the system design stage. So in a particular design, yeah, it is hard to make a decision. Okay, it is hard to make a decision. What we are doing. So now there are most of our designers, what they will do. So initially I will tell that. So when you are going to do any project or any building embedded system, it is going to have a group. So different person in a group will be having a different approach to that particular building the embedded system. When you are going to have the different approach by the different person in the team, what will happen? So the designer is going to switch between the different models. So one person may come up with, so this particular model is correct. Other person will tell you that this particular model is correct. So the varieties of models is going to be switched, because I will tell my design is correct, because as a human tendency, when whatever I'm going to do, I am going to feel that whatever I'm designing, that is right. So as that is a human being tendency, that's it, nothing else. So now when it becomes in that particular manner, so the designer is going to do what? The designer is going to switch between variety of models. From what models, it is going from requirement specification to the implementation aspect. Okay, it is going to be done from requirement specification to the implementation aspects. But when you take the SDLC, so if you take the SDLC, so the requirement which you are going to have, the requirement which you are going to do, requirement and specification, it will be coming in the first stage of your segment language. But if you take the implementation, so your implementation comes in the first stage, right? So now, if I use this particular model, what are the problems I'm going to what are the problems I'm going to face in my implementation stage? That I come to know only at the implementation stage. Okay, that is I'm going to come to know only at the implementation stage. So the object, so that particular reason, what will happen? So at the specification stage, only functionality of the system is focus, not the implementation information. Okay. So what will happen in the beginning of your either it may be a software development lifecycle or it may be a hardware. Both are same, because whenever you are telling the software development lifecycle, you are going to have the requirement, right? So you are going to have the requirement. So when you are going to have the requirement, I will tell you that this particular system requires this particular hardware or this particular processor, and for this particular processor to work, I use C language, and this and different IO ports should be there. So as that is my way of weaving that particular embedded system. But it is not the same with the other person. The other person tells that if I use this one, this may be the problem which may occur. So that you come to know what are the problems you are going to occur, what are the issues you are going to face. So that all these things you are going to come to know only during the implementation stage. So that you are going to come to know only during the implementation stage. So when it comes to the implementation stage, the exact system component which you are going to use. So you are going to have the implementation. So the exact system component is revealed there. So here you are going to have the exact system component which will be relayed. The system component is revealed. So now once it is revealed, so now what the designer has to do? So the designer has to switch to a model capable of capturing the system architecture. So I have designed the model, but at the implementation stage, these are the necessary components which are available in the market. Because as a designer, what I want one transistor, one software should be there, one firmware should be there, like that I will tell. But whether that particular thing is there in the market or not, I will not come to know. So that I come to know only at the stage of the implementation stage. So whether that is there in the warehouse, whether I can use that particular component to make my software embedded system to work, no. So the designer is going to come to know only at the what stage? Only at the implementation stage. Okay. So then if that for that particular model designed, if that particular component is not available, then what I need to do? Obviously, I have to change the design. Then obviously I have to change the design. So changing the design is nothing but I have to switch the model. Okay, the model I have built already. So that model is not feasible with the component which is there in my warehouse, which will be coming at the implementation stage. So if that particular model I cannot do it, if that particular components are not there for that particular model, so what I need to do, I need to switch to a model which will be having the system, proper system structure, which is or whatever the components which is available in my warehouse. So that's what it is going to tell. So after selecting the model, okay, so I will tell that this is the type of the model I am going to use, so it will work fine. So next, the main issues which are going to come in your selecting the architecture. So now if you take the model always captures the system characteristics, that's it. So it is going to capture only the system characteristics, but working it will not take. So it is tell that this is the characteristic of this particular processor. So it can store up to 32-bit. It can store. It is size of 8-bit. It's having the RAM of 64 kilobytes. It's having the ROM of 128 kilobytes. Like that, I will tell the characteristics of that particular embedded system. But I don't know whether it is going to work or not for that particular application. So, and it will not give the in the model what it is going to give. So in the model, it's not going to provide you the enough information. So it's not going to provide you the enough information. So it's not going to provide the enough information that how the system can be manufactured. So that is what stage? That is at the requirement stage. So that is at the, when you are selecting the model. Okay. So when you are selecting the model, so it is not going to specify you that how the system can be manufactured. So now what the architecture specifies now at that time. So basically the architecture specifies how a system is going to implement in terms of number of types of different components, okay, and the interconnection among them. So what are the different components I'm going to use? So different components I'm going to use and how they are interconnected. So different components and how they are interconnected. So among them. So depending upon that one, there are n number of architectures which are there. So the different types of architecture which are going to have is, one is your controller architecture is there, other is data path architecture is there. So third is complex instruction set computing is there. So next, reduced instruction set computing, which stands for RISC, is there. Apart from that one, you are going to have very long instruction word computing is there. That is called as VILIW. So next is single instruction, multiple data instructions are there. So that I think you have been studied in your computer organization. So next is multiple instruction, multiple data are there, MIMD. So these are the most of the commonly used architecture in system design. Okay. So what are the commonly used architecture in the system design? Your controller architecture, data path architecture, complex instruction set computer, which stands for CISC, reduced instruction set computing, which stands for RISC, very long instruction word, which stands for VLIW, single instruction, multiple data, SIMD, and multiple instruction, multiple data. So these are the commonly used architecture in your system design. So this is with respect, this particular architecture is with respect to the processor, okay, how it is going to work, or the controller. So if you take any microprocessor or microcontroller, if that particular microprocessor or microcontroller has to work, what is the architecture I have to make use of? So what type of architecture I have to, it will be suiting for my design, what I have been designed. So that I should know properly. So that particular design depends upon my application. So if I have the more control in my application, more number of controller architecture should be there. If I have the more control operations are there. So if only data flow is there, then I can go with a data path architecture only. Okay. So now when you are going to have this particular type of architecture which are specified now, so these, they may fall into some of the applications specific architecture class. So it is going to tell you that it is going to have this application specific architecture class. So that means what? So when you are talking about the application specific, so it is nothing but your controller architecture. So your application specific stands for controller architecture. So now, why the controller is required? So because the controller is required as and when the event is occurring at the outside environment. So simultaneously the system has to take its decision and it has to respond to the external event. Okay, responding to the external event. So apart from the microcontroller, the rest which are there, the rest type of architecture which are there, which will be falling under general purpose architecture class. Some will be coming under microcontroller application specific general architecture class, which will be used, which will be by controller architecture. Some will be falling for your general purpose architecture class. Okay, so your general purpose architecture class are nothing but your complex instruction computer, reduced instruction computing, and parallel processing class like VLIW, it stands for very large instruction word, SIMD, which stands for single instruction, multiple data, MIMD, which stands for multiple input, multiple data. So now once you have done, so what is the control architecture implements? So if you take the controller architecture, as the name indicates, as the name tells, it is controller, control. Okay. So wherever you are going to have the control type of instructions, okay, so, or branch instructions you are going to have in your control statements you are going to have, right? So wherever you are going to have the control statements. So control statements are nothing but what? Decision making. Wherever you are going to have the decision making to take place. So now they are going to make use of this particular type of controller architecture. So the controller architecture implements what? So it's going to implement the final state machine model using the state register and two combinational circuit. So as you know that it's going to make use of the state register. Okay, so they are going to have a number of registers and two combinational circuits. So in the combinational circuits which you are going to have, so what is the state register is going to tell? The state register is going to tell that what is your present state and the combinational circuits, how it has been improved. So can anyone tell what do you mean by combinational circuit? What's a combinational circuit? Can anyone tell that one? Since you have read already two different type of circuits, one is combinational circuits, other is sequential circuit. So can anyone tell what do you mean by combinational circuit? So your output depends upon the present data as well as the previous data. What type of circuit is that one? So now, whether it's audible for you people? Okay, so here the state registers what it is going to hold. So it is going to hold the present state. Okay, the state register is going to hold the present state at what state you are in, and some of the combinational circuits. So the combinational circuit, for what purpose you are going to make use of the combinational circuit? You are going to make use of the combinational circuit to implement the logic for the next state and the output. So basically, whenever you are going to have the embedded system to be built, so you are going to make use of the combinational circuit. So basically, how the combinational circuit works? The combinational circuit works is what? So one of your the previous output will be fed as an input. Okay. So depending upon the previous output, the next output what it has to be generated, that will be calculated. Okay. So that is on the basis of the combination. Okay, combinational or control or decision. So next part type of architecture which you are going to have is data path architecture. So in your data path architecture is mainly implemented for data flow graph. Okay, data flow graph model. So where the output is generated as a result of set of predefined computation on the input data. So in the data path architecture, what will happen? I'm going to tell you that it is A plus B. That's it. So output is equal to A plus B. So that is predefined now. So now, whereas irrespective of the area, there is no control over the data. So just you are going to give the input. Depending upon the input, what you are going to give, the computation is going to take place, and it is going to generate the result. Okay, what is happening? So now, whenever you are going to have the data path, so your data path which you are going to have, it is going to represent a channel. Okay, the data path which you are going to have, it represents the channel between the input and the output. So what it means? So you are going to have the input. Okay, so you are going to have the input. So here you are going to have the output. So it is going to provide the channel here. Okay, it is going to provide you the channel. So the channel what you are going to provide. So where the data will be flowing here. So in the channel, the data will be flowing. The data will be flowing. So now, so what are this particular data path architecture consists of is the next thing. So in data path architecture, the data path may contain registers, it may contain counters, it may contain register files, it may contain memories, it may contain ports it will contain. Along with those things, it may also contain the high-speed arithmetic unit, because some arithmetic operations has to be done. So to perform that particular arithmetic operations, you require the arithmetic units. So now whatever the ports you are going to have, the ports what it is going to connect, the ports basically connect the data put to multiple bus. So you're going to have the different buses, right? So you're going to have three, which have been come. So that is three different buses which you are going to have. One is your address bus, second is your data bus. Okay, so third one is your control bus. Okay, that we have came across, that you people have come across. Okay, so third one is your control bus. So these ports is going to connect the data but to multiple buses. So whatever the data you are going to have, so this data will be flown through using the many multiple buses. So multiple bus means what? Here which is only data bus which you are going to have, because you have to concentrate only on the data here in the data path architecture. Okay, so your data is nothing but what? It is nothing but a channel. So where it is a channel between the input and the output. So in between some operations you are going to perform directly, and you are going to send the same data along the channel. So that's what your data path architecture is all about. So next comes when it comes to the finite state machine data path architecture. So what this particular finite state machine architecture is? So basically, if you take the FSM, that is finite state machine. So in the finite state machine, what it is going to tell? So it's basically combining the controller architecture with data path architecture. Okay. So whatever finite state machine data path architecture is going to tell is basically combines. What it is going to combine? It is going to combine both your controller architecture as well as the data path architecture. So that means it requires what? Data plus decision on that particular data. It requires the data plus the decision which you are going to take on that particular data. So what it is going to implement? So what your finite state machine data path is going to implement? So it basically implements a controller with data path. Okay, so it is telling that it is going to implement the controller. So controller is nothing but what? The controller is nothing but the decision maker. Yeah, the controller is nothing but the decision maker, depending upon the decision. So that means if A is greater than B, I will make some operation to be performed. If A is less than B, I will make some operation to be performed. So if I am sensing the temperature which is greater than 40 degree, if it is AC as AC, then I have to reduce, then I have to increase my AC, okay, to certain degree centigrade. So that's what it has to do. So now for that particular things to happen, what the controller needs to generate? Basically, the controller needs to generate the control input. Okay, the controller generates what? The controller generates the control input, where the data path process the data. That's it. So controller is control input is going to have, data path is going to have data input. So now next comes what the data path consists of. As the name indicates, data is nothing but you are sending the information. But what do you mean by data path? Basically, if you start talking about your data path, the data path contains two types of I/O ports. So one of which one acts as a control port for receiving or sending a control signal from or to the control unit. So one port, it is going to have two types of I/O port. Okay, so one is our control port. So one is your control port. So where it is going to receive or send the signal from which? From control unit. Okay, so it's going to have control signal. What is operation? It won't send or receive the signal from where? From receive control signals to whom it is going to send? To controller unit it is going to send. Okay, and another port is there which is referred as second I/O. Okay, second I/O port interface is there. So here it is a data path with external word for data input and data output. That means the I/O port, one is generating within the embedded system. The other port which is there, so it will be to the external world. So the port will be for external world here. So the port is for external world which you are going to have. So depending upon the external world data, what type of data it is coming, I have to process that one, and depending upon the type of the conditions which is I am already pre-programmed, so that particular controller it is going to work. So that is depends upon your data path. Okay. So next, when it comes to the complex instruction-set computing, so this is already you know that one. This basically use the instruction set representing complex operations. That means it includes both the data which is going to retrieve from the memory and to place it onto the register. So it is going to perform 2 or more operations in a single instruction, or in some of the textbook it is going to tell in the different fraction. So it is set to perform a large complex operation. Okay, so large complex operation is nothing but what? 2 to 3 operations will be completed in a single instruction. In a single instruction. So that means what? I have to move the data from memory. So I have to move the data from memory to register. Okay. So now when you want to move the data from memory to register, particular register, so first it will move the data from the memory to the accumulator. So in your CISC machine, and from the accumulator you have to move to the register. That is what the process. So now those things. So now in your RISC machines, if you take, so if you want to move the data from memory to the memory to the register, or register to the memory, you have to make use of load and store instructions only. That is in RISC. Okay, that we have seen in your ARM microcontroller. So now what is the problem you are going to have? So there is use of single complex instruction. It's going to do what? It's going to place a multiple simple instructions. So that is nothing but what? So it's going to do a multiple simple instructions instead of doing multiple operations. It is going to do a single operation. So if you are doing it a single operation, what will happen? The consumption of the cycles to execute that particular instruction will also get increased. So, but the program size will get reduced. It will reduce the program memory access, and program memory size. So it is going to reduce the program memory access and program memory. It is going to reduce that one. So, but what is the problem we are going to have? So it requires the additional circuitry for that one. So it requires the additional circuitry. So here, whatever the circuitry you are going to build, it is going to build with respect to silicon. So that's what they are going to tell with respect to textbook, that is a silicon. So your silicon is nothing but what? It's going to be additional circuitry. It requires for what? For implementing the decoder, microcode, and to decode encoder. Also, you should have additional circuitry for encoding the instruction, decoding the instruction. Okay, so encoding and decoding, you require that one. So when you take the data path of this CISC processor, so the data path of your CISC processor is normally it will be a complex one. So the data path will be normally it will be a complex one which you are going to have. Okay, so that is what it is. So you know already the reduced instruction set architecture. So now it requires execution multiple RISC instruction to perform a complex operation. So that means multiple simple operations are performed to do a complex operation. So that's what your RISC machine is going to tell all about. Okay. So whenever you are going to have the RISC machine, so the RISC machine, what it contains, the RISC instruction set architecture is normally operated on registers. Okay. So it will be normally operated on the registers. So now when you are going to have normally operated on the registers, so when you are going to have the multiple registers, obviously I can use the pipelining. So as we have known, what do you mean by pipelining? Pipelining is nothing but overlapping of the instruction to complete an instruction in a single clock cycle. Okay, so that's what the RISC machine is going to be make use of. So next is Verilog instruction word operation. So in the Verilog instruction word architecture, so it's going to make use of the multiple functional units in the data path. So that means multiple function units mean what? Some functionalities were designed to perform only the arithmetic operations. Okay, so you can see it here. So you're going to have the function, so if you take the processor, so many function units will be there. Okay, so if you take the IO connect, so this will be using for arithmetic and logic operations. Some it will be used for floating point operation. Some it will be used for multiplication operation. Okay, some it will be used for your memory related operations. So the functionality is totally a different one to perform individual instructions. So the functional functions are there in your data path. Okay, so you are going to have the data path. So inside that particular data path, it's going to have the multiple functionality to perform the individual function. So for arithmetic function, only one particular functionality is there. For logical operation itself is one functionality is there, and for control operations itself, it is going to have one functionality is there. or if you want to have the floating point operations, that is required in a different function unit, what is going to have. So now when you take the very long instruction words, instruction packages, so one standard instruction per function unit of the data path will be there. Okay, so that's what. So next is your parallel processing architecture. So the parallel processing architecture, you are going to have two different types measure, which will be standing for single instruction multiple data, so and multiple instruction single data. Okay, so now in your parallel processing architecture, what it tells, so it is going to tell you that how to implement the multiple concurrent processing elements, and each processing element may associate it with the data path which contain the register and the local memory. Okay, so each and every, I am going to do the multitasking. When you are doing the multiple tasking, each processing element which you are going to have, so that particular processing element will be having its individual data path. So that individual data path will be having its own register as well as the memory. Okay, so it is going to have like this. So if you're going to have the data path, now if you're going to have the data path, so I'm going to have some processing element will be there. So data path which are going to have the register, so and they're going to have the memory. So that means parallelly it will be having many things. So register, memory, it will be having. Okay, so it is like this one. So now if you are going to have a single instruction, so if you are going with a threading, so threading is nothing but what, within a single process you are going to create multiple threads. So it is similar to your SIMD. So you are going to have a single instruction, here it is going to operate on a multiple data, single instructions, multiple data. So a single instruction is executed in parallel with the help of the processing instruction in this one. So now how the scheduling will be done. So your scheduling of the instruction will be done by the single controller, performed through a single controller itself will be there, single processing element will be there. So that is performed only through the single controller. So now when you are going to make use of the single instruction multiple data, so it is going to be make use of reconfigurable processors. Okay, so on the other end, when you are going with the multiple instruction multiple data, so it is going to tell you that what, so different instructions are going to run at a different point of time. So when you are going to have the multiple MEMD architecture, so it's going to be basis for multiprocessor system. So what do you mean by multiprocessor system? Anybody having any answers from your side? Since already you know that what do you mean by multiprocessing in your from your operating system point of view. So can you tell what is the how your multiprocessor system is going to look like? How the multiprocessor system is going to look like? So whether it is going to be in a single system, same system you are going to have, whether it's the same system or a different system. Can anyone tell the answer? When it comes to the multiprocessor, it's going to same system or a different system. You have the two terms. One is multiprocessing and multitasking. Can anyone tell what is the difference between multiprocessing and multitasking? Multiprocessing is a single system, right? Multitasking system for different system. Okay, so that's what it means. So it is going to be behind the same system. If we take with the multiprocessor system, it is like a process divided into number of threads. You are going to have the process. Inside the process, you are going to create a number of threads. Okay, thread 1, thread 2, thread 3, thread 4. So whereas in your multitask, it is going to allocate a job to a totally different node in your multitasking. Okay, so that's what the multitasking is all about. So now next about after selecting the architecture. So in the selecting the architecture, we have discussed about controlled architecture where it is going to have the decision making, then the data path architecture, then the finite state machine, and you are going to have the CISC type, RISC type, VLIW, and parallel processing architecture. So in the parallel processing architecture, we discussed about SIMD and MIMD. So apart from that one, the next issue which will come after selecting the architecture, what type of language I have to make use of. So what type of computational model I have to make use of in your language. Okay, so what type of computational models and maps it to that particular architecture. Whether that particular architecture is going to be suitable for the language, but for the code what I am going to run from that particular language. So now there is no set rule are there. So if you are taking the model, So the model can be captured using multiple programming languages. Okay, so there are 9 number of programming languages which you have come across. Like you can use C, you may have use C++, or you can have C Hash, or you can have Java. So it is going to be a totally a software implementation. Okay, and if you take the hardware implementation, when you want to write a code for hardware to control the hardware. So to control the hardware, if you want to write the program, you have to write the languages which are there. For that one is BSDL, System C, Verilog. Okay, so these are some of the languages. So your C will be acting as both, either at the software side or at the hardware side. So if you take the C programming, so C programming, basically it is going to work with respect to hardware also, and it is going to work with respect to software also. Okay, so both the way it is going to write. So on the other hand, if my language, if I am selecting which one is feasible for that one, a single language can be used for capturing a variety of models. So that means I will select a single language. That particular language itself has to accommodate or capture or work efficiently for the different models. So if you take with the computational model, certain languages are good. Okay. For example, if you're going with a C++, so C++ is basically good for object-oriented concept. Okay. So when you are going with the object-oriented concepts, so if you go with the object-oriented concept, so you're going with the C++ is a good candidate. So now only prerequisite in selecting a programming language for capturing a particular model is that language should capture the model easily. So that means whatever the language you are going to have, that particular language has to understand that particular model, or it has to understand that particular hardware or behavior of the hardware which you are going to have. So the behavior of the hardware has to be effectively understood by that particular language. Okay. So next, it is going to partition requirements for into software and hardware. So if you're going with the requirements, so partitioning system requirements. So it may be possible to implement when we talk about the embedded system. So when you talk about the system requirements of the embedded system, so it's basically categorized into two types. It is going to be implemented either at the software side also, or it is going to be implemented at the hardware side also. So now when you are implementing the system requirement at the hardware side, and it is going to be implemented at the software side. So normally when you are implementing it at the software side, so they are called as firmware in your embedded system. The software which you are going to have to build, so the firmware designer, they are going to call it as. Okay. So normally whenever you are going to hear the name as firmware, it is relating to the embedded system. But firmware is a software only, which you are writing for the embedded system. So now it will become difficult for us which one to figure out, and which one to opt it. So various hardware software trade-offs are there for making a decision on the hardware software partnering. Which language I have to use? If I use that particular language, how that particular hardware is going to work. So for example, if I'm going to have the efficient look and feel, my front end should be good. So now if I backend, if I go, so backend will be always, if I take the any software, so it will be having the front end and the back end. Okay, so back end. So if you take the normal data recovery software, if I take, for example, okay, for example, if I take the data recovery software, so the application should look good. So it will be front end. And the data should be recovered from where? The data should be recovered from your hard disk. So your hard disk is a hardware. Now they should have an interaction. So these two has to be effective, means what? Both has to be written in a single language. Both has to be in single language if it has to be effective. Okay. So now if both the language is not supporting, means what? So I'd look for the language where other language can be accessed. So like Java, if you use, there is a Java native interface is there, which will make use of that particular Java native interface, and it will access the C code. So your C and Java can be linked together using the Java native interface. So that if you want for higher knowledge, you can go with and you can read it. So that is called as JNI, which stands for Java native interface. Okay. So you can go and check with JNI. So that you take it as an assignment. So that stands for Java native interface. So that stands for Java native interface, which you are going to have. Okay. So that's how it is going to happen in your So that trade-off has to be taken for decision making on the hardware software computation. Okay, so that is about your some of the fundamental issues which you are going to have when you are designing the when you are designing your hardware. Okay, so I will stop here. So if you have any doubt, you can ask. If anybody having any doubt with respect to the topic which I have covered, so you can ask there. No. Anybody having any doubt? So now, anybody having any doubt? I'm asking. If you have any doubt, you can ask.
No, sir.
Okay. So just go through it once. So because if you go with the embedded system, so it is very interesting to work. Okay. Because most of the embedded software or most of the automotive vehicles, and we don't know when your service-based companies will stop. Okay, so just you shift to the embedded side. It is a product-based companies. Whenever you want to write with respect to a product-based means what? There the embedded system will come into the picture exactly. Okay, so that you should know. So